I am Max Grunwald, and I'm here today to give my research presentation for the George A. Jeffrey Nano Explorers program. This presentation is about the work done in the Ferraris Research Lab over carbon nanotube poly-3,4-ethylene dioxythiophene as an electrode for supercapacitors. First of all, I would like to introduce what supercapacitors are. Simply, they are energy storage devices. They combine the benefits of capacitors' high specific power with rechargeable batteries' high specific energy. They're used in things such as cell phone battery backup, off-grid energy storage, and hybrid electric vehicles. This car right here is a Honda Insight, and it uses a supercapacitor in order to store energy and use it for acceleration, and it recharges during deceleration in staying at constant speeds. This over here is Ragone plot. It shows the power density versus energy densities, and electrochemical capacitors help bridge the gap between batteries and capacitors. The current goal is to raise the energy density and power density by making supercapacitors. So to understand the mechanics of how to increase both the power and energy density, you need to understand how supercapacitors work. Supercapacitors store energy through capacitance, which is charge stored per unit voltage. Also can be expressed as the physical dimensions. Increasing the surface area of the plates and decreasing the distance increases the capacitance, which in turn raises energy, because energy can be expressed as 1/2 capacitance times voltage squared. An increase in energy will also mean an increase in power. So now you need to understand the differences between traditional capacitors and supercapacitors. Traditional capacitors store energy simply from applying a potential difference across these two plates to create an electric field to store charge. Supercapacitors work differently. Supercapacitors work by including a highly porous material in an electrolyte solution. Upon charging, the ions in the electrolyte solution end up getting associated with oppositely charged plates. So now there are actually two capacitors in series with one another, with the distance in scale of nanometers or even angstroms. This causes a great increase in the capacitance, as making it to levels of farad to kilofarads over the regular capacitors, pico to microfarad levels. So first of all, there are two different types of capacitors, one of which is the electric double-layer capacitor. Charge storage is solely electrostatic between the ion-electrode interface. They have very high power density and they have high surface area because of the porous carbon. However, because it's all electrostatic, they have low energy density. However, there are also pseudocapacitors, which work by having reversible redox reactants along the surface of the electrode. They have very high energy density because of the chemical reactions occurring between them. However, the high cost of metal oxides and the eventual degradation from continuous cycling of the electrodes ends up causing them to degrade. Now, we worked with composite supercapacitors, which are a combination of both. They gain the advantage of the electric double-layer capacitor and pseudocapacitors by having high surface area stability, power, and energy densities. So now that the basics are covered, I'd like to go over my research goal. We deposited PDOT via electrochemical polymerization onto the carbon nanotubes, and then we tested the supercapacitor's performance via cyclic voltammetry and constant current charge discharge. We used both the carbon nanotubes and the PDOT to enhance the electric double layer and pseudocapacitive properties. The carbon nanotubes are extremely porous, and that enhances the ion diffusion, which raises the power and helps the electric double layer properties, and so faster ion diffusion. Also, the carbon nanotubes served as a backbone for the PDOT to be deposited, and so when they were deposited, it allows it to be de-doped and doped along the surface, which raises the pseudocapacitive properties and raises the energy density. So this slide simply depicts an experimental process. We started with carbon nanotube synthesis via chemical vapor deposition. Then the PDOT was then deposited on the carbon nanotube coated electrode. Then we made the supercapacitor and tested it. So over here, these are images of the after chemical vapor deposition. Over here, you can see the forest of carbon nanotubes all sort of accumulating. And over here is a zoomed out version of it. In the background, you can see spectral carbon fiber paper. These are the fibers of it. And all the forest ends up growing sort of along the fibers, so that's why it appears all scattered. After chemical vapor deposition, then polymerization occurs. We use two different types of tests, cyclic voltammetry and chronoparametry, and the steps of them are over here. And over here to the right is this diagram of the setup we used. We used the working electrode was the carbon nanotube coated electrode, and it was held by stainless steel backing. The reference was a silver plus, and the counter electrode worked as an electron sink. It was carbon felt, and it was wrapped in a platinum mesh. All of this occurred in a 0.01 molar ethylene diethylthiophene, and that was the monomer P dot. And then there was also 0.1 molar tetraethyl ammonium tetrafluoroborate, or TbF4. This occurred in acetonitrile, and that gave the electron. Over here, this is the after polymerization. This is the chemical equation of the polymerization. And over here depicts the cyclic voltammetry results. As you can see, the P dot is sort of accumulating on top of the carbon nanotubes rather than coating them. It's sort of just clumping on top. However, the chronoamperimetric results created a more desirable and porous polymer, which coating along the nanotubes. So we use these when fabricating the coin cells instead. This is simply coin cell assembly. We worked with a stainless steel outer, added 2 spacers, an electrode. Then the electrolyte solution of 1 molar TbF4 was added. Then a spacer was added to make sure the circuit doesn't short. Second electrode, 2 washers, and then 2 spacers and a washer to make sure that the electrodes are held in place and constant contact is added. And then an inner was added to cap it. Then it was put in a manual crimper, and then it was sealed, and this over here is a completed product of a coin cell. Then we went on to testing the coin cell. We used 2 types, cyclic voltammetry, which is a voltage sweep, and that is used for determining the specific capacitance. We tested at different scan rates, 10, 25, 57, 100. And then we did constant current discharge, which ends up charging it from -1 volt to 1 volt, since that's its voltage window. And we ended up finding the discharge time to find the energy and power density. All of this was done using the Argon supercapacitor testing system, as depicted there. So now on to the results. The results we had were quite good considering the graph. It's very flat and box-like, which is indicative of an electric double layer. And we ended up graphing the current versus scan rate in order to get the slope, as seen here. Then we used these other equations from that graph in order to determine the specific capacitance. We got a specific capacitance of 59 farads per gram, which is really good considering that carbon nanotubes deposited just on SpectraCarb end up having a capacitance of only 3 farads per gram. Over here are the charge-discharge results. The charge-discharge test helped us find the power and energy density. We ended up determining the discharge time. And after that, we found the energy density, and then after that, it's simple to find the power one. And at 10 milliamps, we ended up getting the desirable energy density of 11 watt-hours per kilogram, and a power density of 1.7 kilowatts per kilogram. So in summary, P dot was successfully electrodeposited onto the carbon nanotube backbone via electrochemical polymerization. The carbon nanotube composite gave us a specific capacitance of 59 farads per gram, and constant current charge-discharge test gave us an energy density of 11 watt-hours per kilogram, and a power density of 1.7 kilowatts per kilogram at a current of 10 milliamps. And I'd like to thank Dr. John P. Ferraris, my mentor Jaleesa Bonzo, the Supercapacitors Group, the Nano Explorers Program, and everyone in the Dr. Ferraris Research Lab.
Questions? Yes?
Yeah, very interesting. For the electrochemical deposition of the E dot, you said you didn't use those for the coin testing.
We didn't use the cyclic voltammetry results. We used the chronoamperimetric ones just because of the scanning electron microscope images. It looked more desirable.
Right. Could you do some chemical analysis? You said that there was some inhomogeneity of the E dot or the P dot deposited. Could you do some chemical analysis, or did you think about doing some of that to see if there was any kind of
we haven't
structure?
We haven't done that yet, so that could be future work.
Any more questions? Okay, if there's no more, let's